Alright, should be making a video. Do a little quick check. Draft physics and such. Looks okay. So we're going to talk about electrons and how they determine their mass, but there's a lot more to the the experiment really. It illustrates a lot of things, so I'll try to get to that. So there's 3 videos really. The Hilster guy made a video, and then it links to an old video made in the 50s or whenever, 60s. That was very good actually, so I might play some of that. And then there's a 60 symbols video on electrons that's just terrible. And so between the 3 of these videos I should be able to make a point. So I think what we will first do is do the old video. And it's very interesting, this electron gun. Points out that the anode is here, cathode is close, and the electrons come out of this little hole, apparently are to some extent deflected by these little plates to keep them from diverging, I suspect, which just brings up a whole lot of points about why, about experiments where they would actually shoot electrons, the free electrons, and see how far they can go and what happens to them. Because frankly, they should be able to get them in a pretty tight beam, because they can, unlike light, you can push them into locations, and you should be able to get them moving fairly straight to start with anyway, and you would learn something about how much they diverge. So maybe this stuff has been done. It's just that unfortunately we don't have a lot of these experiments done in the modern era, done with the clarity that this was done. So maybe we'll go back to the beginning. I don't want to make the video too long, because this could take an hour or two, but unfortunately.
To see what happens to electrons when they are acted on by electrical forces and magnetic forces that we can produce and measure.
So the getting acted on means they're obviously accelerated by the electrical forces, so they're forced to jump across an electrical potential, like a spark. So they're initiated with a momentum, and then the idea is some of them, you fool them, so somehow they think they're jumping to the plate, and the plate's not there, and they end up freely flying. They don't get to hit the anode. And I don't know exactly how they did that, but they have this little cone. I don't know exactly how the cone works, but it is interesting.
One of the things that we'll be able to...
So anyway, so the 2 forces, the electrical force is just the propelling force. Then the rest of it's the magnetic field being created by the 2 coils. And there, in my opinion, is a complete misunderstanding of the function of those coils.
From our observations is the mass of an electron. This tube contains a little hydrogen, and over here there's...
So the hydrogen just exists to make the beam visible. So you're just putting something in the vessel so you can see the electrons, which are crashing into the electrons of the hydrogen and creating photons in that process. So in a sense, you should be able to change the color would be half dependent on the pressure of the hydrogen atoms. So that's going to be one point of color, and I would argue that another point might be the velocity of the electrons, that you can change perhaps the color, the intensity of it maybe, by changing the velocity of the electrons, the voltage they're jumping.
Gun aimed upward. The source of electrons is a heated cathode at the bottom of the gun.
So, you just heat something, it produces electrons, they're escaping at a velocity, and then somehow, this just seems like a funnel, it's a screen of some kind, but obviously there's a little hole at the end, it seems. Those are where the electrons are coming out, so somehow they've created a device that creates a pretty good little beam of electrons. And these 2 deflectors are keeping the beam from diverging this way, which is the way they're looking at the beam. So they want the beam to be as tight this way as possible. It can expand this way, as you can't see that. Okay, but you could see expansion this way. So I imagine that's what the 2 plates are for.
The electrons are accelerated upward by a potential difference applied between the cathode and the cone-shaped anode above it.
Yeah, I don't know. Potential difference. I know that everybody's supposed to know what that means, but they should just say voltage difference. The voltage is causing the effect. It should be mentioned that it's voltage.
The accelerating potential we read on this meter. And once we have a moving stream of electrons, we have a second way of controlling their motion, namely by a magnetic field. We know that a charge moving across a magnetic field has a deflecting force on it. We use these coils to produce our magnetic field. A current flowing around a circular coil like this produces a magnetic field at the center that has a direction perpendicular to the face of the coil.
Okay, so she's doing the right hand thumb rule thing just to throw that in, but she doesn't say it overtly. She's just doing it to illustrate something. Now, obviously this experiment will demonstrate there's no thumb motion. There's no motion of a field going in any direction. The electrons would obviously be pushed if there was any motion. So there is no motion inside the coils in a direction. And so this is a huge misunderstanding of the mechanism, in my opinion, is everybody keeps talking about these moving fields. There is no moving field. The iron filings are not showing you, pathways. They're just showing you what little dipole magnets, how they'll line up in the field. What's the pressure on the magnet? Does the magnet sense a bias? And the whole point is it's not sensing a bias. There is no directionality. There is no flow. There is no anything to move it. It's being equally affected in both directions, and that's why it lines up perpendicularly. That's why it is neutral to the field. If it was pointing towards something, then you could argue that there was an attractive force there. The attractive force is different. That the thing, the poles are always pushes. I have to keep saying that over and over again. The point is the field isn't creating magnetism. The field is magnetizing what you put into it. That magnet becomes the strong magnet. So if I shove a piece of iron inside of that coil, the iron will have all of its bits lined up. They won't be flowing, they won't be pushing, they'll be aligning. And once they line up, they become a very powerful magnet. And their magnetism is much stronger than the magnetism of the coil. And you'll have a byproduct. You will have motion, but that's just because of once the magnet starts magnetizing, it wants to get more magnetic. It moves towards the thing that's magnetizing it. All right, so we'll go back to the D. Hilster thing, I think. So this is a Google. I mean, his son ought to tell him that he can post links in the description. He posts the written links, and you have to type all the crap to get to the link. It's not very clever. It's not the best. It's so. Get up to speed. You can post links, actual links. You don't need to have people typing, obtuse YouTube addresses and Google addresses. He really should tell his. He really should fix it. It's just almost obnoxious. Here's a link that you have to type. It's just so overtly internet lame. All right, so here's the two coils. Now they're aligned in the same direction, which, again, they're trying to imply that there's a north side and a south side and all this stuff, and there really isn't. The field, you can see it in a sense around the coil here, that the magnets are lining up in a circular pattern. They're not lining up with their north ends pointing or their south ends pointing, indicating there's a strong bias. If there was a strong bias in the field, then they'd line up on that strong bias. But there clearly isn't a strong bias, so there is no north side and south side to the individual coils. And the north and south part only happens when the magnetism is created. When you put the iron filings in, they create a magnet that has to be oriented to the field. But without them, from a monopole's point of view, from something that isn't polarized, that isn't a magnet, that doesn't have a dipole, from a monopole's point of view, the field is even. It just stays where it is, in a sense that it's even pressure. So if I were to, let's attempt to do this, it might work. Take advantage of this transparency feature. This is about right, I think. Let's see if I can actually draw over this drawing. This would be challenging. So you can sort of see it right, here. You can see this little, it's like a loop going around. Okay, that's got to be more, well, it might be dark enough for you to see. All right, so everything is lining up in rings. So if it was a polarized field, that is a north-south field, then the little bits would be lining up, as magnets with their north-south facing somewhere. And they're not. They're lining up like compass needles pointing at each other. So there's no bias in this field. So what's going to happen, save this knowledge for later kind of a thing, is the field, the energy that's going to hit the electrons is always going to be, because the globe that's going to be inside this coil is much smaller than the coil in diameter. And the stuff that's going to hit it is going to be radial. The force coming off this coil is radial. It's coming out, radially out of every section here. Okay? So it's, they're all straight lines and coming out of the, so here's the coil. The rays are coming out straight this way, all the way around. So all the way around, going up the thing, the rays are coming out this way. And the same thing's true for a radio antenna. That's how the rays are coming out. And they're not all black on one side and all red on the other side. They're not all positive on one side, negative on the other side. They're not all north on one side, south on the other side. They're clearly a mixture, and exactly an even mixture from a distance. So if I have a magnet here, the magnet will line up, north-south. If you think of this is north and south. It'll line up this way, all the way around, because it's going to be an even field from its perspective. So these rays are black, red, black, red, black, red, black, red. They're north-south, 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 going radial around. So if you were to look at it this way, there would be a bunch of red line, black line, red line, black line, red line, black line. It's an even field. And it's critical to understand that. So that's what's going around in that loop. So what's affecting, let's try to make this a hair darker. And which way do I go here? You have to be in the right place somehow. I have apparently done something incorrectly. Oh, I have to be here. Okay, there it is. Alright, so now you can see that a little better. Alright, so the field is going to be radiating in all these directions. The little bits coming out. And so the ones that are going to hit the electron are coming from both sides evenly and at these directions. So they're being directed this way down. And the combination of that will create your Lorentz force, your Lorentz force, down. Okay? So the electron will be, as it's moving, it's going to feel that force from every location like gravity. So from every location, the net field will be like gravity down towards the center. So you can sort of see that here. Okay, it's the energy is coming out radially, and that the radial lines will hit here evenly. And you can also sort of understand that if I move the globe this way or I move the globe this way, it's not going to matter too much, because the strength of this force will be the same as having the more exposure to this one. So I'd have less exposure to this force as I get closer to it, and I'll be exposed to more rays from this direction as I get further away. So it's the same as the light bulb argument. Between two light bulbs, you can never, you know, two equally intense light bulbs, you can't really walk somewhere and get hit by less light. That's not going to happen. So that's how this is really working. As the electron comes up, it's constantly getting hit by these two arrows because it's inside these coils. Remember, it's always inside the coil. So the coil here is pushing that, you know, this force towards the center, towards the center is coming out of the whole ring. So better draw it this way. So the ring, oh man, it's supposed to be a circle. Having a bad back must ruin my ability to draw. So the ring is basically radiating their force all towards the center. Okay, there's no, so you can really get the idea that that's what both rings are doing, and they're doing it, and it's spreading into this middle part. So they're pushing towards the center, pushing towards this center, pushing towards every part of this center line. That's where the rays are all hitting, so to speak, aiming, going. And so no matter where you go, up or down or this way, you'll always be in a proportional amount of force, and you'll be deflected appropriately. So like I said, there is no movement through those two fields. It's an illusion. It's just what happens to dipoles, things that can detect the fact that the rays coming out of the two things they're going you know what I'm saying, they're red black, north south, and the two are out of phase essentially, but it doesn't really, you know, and only a dipole is going to be able to detect that, sense that. But that part, you know, it's just not critical. So why confuse things further? Why create opportunity for confusion? I have to have a bare place for my mouse. It's in my drawing. So anyway, okay, back to the videotape. Maybe I'll take a little break here, organize myself better. Alright, back we are. So again, the field pointing in a direction, that field is incredibly weak, that orientation. And it's just made of the fact that, say if you were to take the exact midpoint of this radial force, the exact middle of it, the middle of it would say this is the north end, this is the south end. The rays would have a bias, a slight bias in that direction. So if you put a magnet in there, the magnet will line up with that bias. But there is no strong polarized field. The field's polarization just has to do with where it starts. So the right-hand rule is essentially made out of a principle where the middle of the magnet, when the coil is this way versus the current going this way, just means the middle of the magnet says right is north, left is south. Okay, the ray I shoot this way, the first ray in a direction is a north ray, and the first ray in a direction this way is the south ray. And that simple little change affects all the magnets. So they end up all lining up north, south, north, south, north, south. So it creates, with something that has little magnets in it, something that has a dipole atoms, it'll line up those atoms, and once those atoms line up, then you've created a big magnet, and that big magnet now filters the environmental forces and creates segregated force. Red all going one way, black going the other way, north energy going one way, south energy going the other way. But the coil doesn't create a segregated magnetic field. It just creates one that has a decided orientation. The first move, like in chess, is white or black. Black right. Right? And that's the way it goes. So if I turn around, black right is this way. So that's the only bias it has. So in this experiment, I don't think it would matter if they turned one of those coils around, because they're moving a monopole. They're moving an electron, and the electron doesn't care about that bias. It's not going to line up with the two pressures. It doesn't have to do the right hand rule. It's just going to do how much. The only energy that's going to move it is the black energy, the repulsive energy, and the south energy that hits it is just going to be converted, deflected. So it'll change what magnetism the electron creates, in which direction, but it will not change how you move the electron.
And a magnitude proportional to the current flowing. This apparatus has two coils, arranged in such a way that there is a very uniform field between them, so that wherever an electron is found within the tube, the effect of the field will be the same.
See, so this is why the illustration of the thumb, the illustration of the lines moving, north end flying into the south end, this circular crap, doesn't mean anything. And that's the part where you can understand how it can't mean anything. As you just said, it's a uniform field. It's almost like an anti-gravity field, in a sense that it's like perfect gravity, in the sense that the radiation will be even from all points. And again, and it's even in both poles, I'm just saying, but the point is the electron only cares about the one force. It's only going to be moved by the one magnetic field, the one element of the force. It only moves towards say moving towards I guess you could say moving towards a south pole. The only reason why it moves towards the south pole is it's not being affected by the energy from the south pole, so it's being pushed. So again, you always have to understand that everything that looks like something moving towards something else or being attracted, you have to look for the push. It's not because there's a bunch of attractive energy. It's because there is no repulsive energy, and that's why it moves into the space. It's because of an absence of pressure, not an abundance of pressure.
Arranged in this way, these are one coil radius apart, are known as Helmholtz coils.
So you can just imagine, just think of see where the coil is, and the rays are all moving perpendicular to the coil, and so you can sort of see that, in the middle of the coil here, in this coil, this would be a perfect center, and you can just move that perfect center everywhere, and you'll get hit by an even amount of radiation in that perfect center. That perfect center line is an even force, and likewise, as you move out from it, there's these other lines at less and less intensity of the force. Well, it's not really less, it's the same amount, because as I pointed out, the closer you get to one side, the further you get to the other, you're being exposed to more angular exposure. The further you get away from something, the more angles that can hit you. If you get close, all of this stuff can't hit you. You get further away, more of this stuff can hit you. And as you get closer to something, you're getting less exposed. I'm just saying it's always even. So no matter where you move, although you're getting closer to one side, you're getting further from the other side, your exposure to more angles of force increases as you get further away. So the net effect is the force is always the same. So in a sense, as she's just stated, it's an even force throughout this inside that entire cone. There's an even amount of exposure. If those two hoops were creating light, the argument would be it's the same amount of light no matter where you go inside those two rings of light. You can't go somewhere where there's more light. And the light is shining in. So it's always moving. Obviously, it has to be coming from the outside in. And that's why the electron moves in, is because it's being moved by the photons, so to speak. You're not an electron, so obviously you wouldn't move, but I'm just saying. So it's completely even, and that's why it creates something that looks very much like the even force of gravity.
You can see that the electrons are going to be moving upward in this direction. The field is horizontal in this direction.
So again, it's just a complete misrepresentation. No, the field has no direction. It's not moving in that direction. It just orients magnets north-south, 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 north-south. It doesn't move magnets in any kind of direction. It just says there's as much pressure on this side of the magnet as there on this side of the magnet everywhere you go. So for any monopole, it's the same amount of pressure, and it's all coming from the inside. So it had this direction idea is just, it's the wrong way to look at it. There's a direction to how the magnet will line up, but there is no impetus to move in a direction.
Perpendicular to the motion of the electrons. To measure the field strength, we read the current in the coils on this meter. I've made a calibration curve showing the magnitude of the field for each value of the current. As you might expect, it's a straight line. In other words, the field is proportional to the current. Now let's turn...
So, and the current is really proportional to the wattage is what you're really after here. So I would, I don't know if that's exactly accurate. I think the more watts you put into the coil, the more you're going to get out of it. So, they don't tell you how many voltage, what the voltage on the coil is. But, it's clear that there's a huge bias for the magnetic field for high current. That's why they have to, when they try to make a single wire create a magnetic field, they have to use an intense amount of current at a low voltage.
Tube. We'll start with no magnetic field, that is, with no current in the coils. As I turn up the gun voltage, which you can read on the top meter, we see the beam of moving electrons. It's visible, or at least visible in the dark.
Yeah, which is really neat. I mean, like I said, it's just bad that you can't see any modern experiments where they do this stuff. I mean, you have to go back to the 60s. I mean, this is very informative. So anyway, I'm gonna take a little break. Oh, smoky. Anyway, vapey.
Electrons make the gas in the tube glow along the path of the stream.
So again, it's not really the gas in the tube glowing. It's really, yes, the electrons are hitting other electrons and photons are being released through those collisions. The electrons are all, they repel each other. When two electrons move into each other, they compress the forces between them, more bounces. And as they're doing that, some radiation escapes between the two electrons at that frequency, and let there be light, let there be X-rays. This device, no doubt, probably creates some of those. So that's part of the story.
That since we know the voltage applied to the gun, we know the kinetic energy of the electrons as they leave the gun. The energy of an electron as it leaves the gun is equal to the energy per elementary charge times the charge. We have 100 volts on the electron gun, and each volt is worth this many.
So I don't follow all this stuff, but I don't know exactly how. I guess the 1 mv squared, 1/2 mv squared is ends up being, this is velocity, not voltage, I guess, and so that's the voltage times Q. I believe that's what you did there.
Per elementary charge And now an electron has one elementary charge, so our Q is 1. And this is the energy of one electron as it leaves the gun.
So the 100 would be the voltage, so the V is voltage, and this little v is velocity. This.
Now let's turn on the magnetic field, which will change the direction of the electrons, but of course won't change this kinetic energy. This time, watch the ammeter at the bottom.
I hadn't seen any videos by this woman before. They didn't leave the credits on here, so I don't know who made it, when it was made, or anything about it. It's just kind of irritating because you know, I think she's pretty good at this.
As we increase the field, we increase the deflecting force on the beam.
So you can't get, you know, it's just right there in your face. So there's a bunch of, you can just see it. The force is pushing from both of those coils, and it's just pushing. Rays are hitting the electrons down, 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 down. There's no this way going on. It's just this way, down, 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 and from both sides. And you just combine these two vectors into this vector, and you have gravity, essentially. Something that looks just like gravity. Quite interesting here where it avoids going into the anode, you know, and does create a secondary loop. But again, we don't know how long these electrons survive, how their velocity, how much distance you can get out of their velocity, how much their velocity degrades with each meter of distance.
Remember, the magnetic field is perpendicular to the path of the electrons everywhere on the path.
So again, she's saying it again, the magnetic field is perpendicular this way. No, it's coming out perpendicularly from the coils. It's coming out as rays. You know, again, there's probably a good way to illustrate it, but you know, a piece of paper, I guess I could just poke a hole through it, and you have to think of it as just rays coming out this way, all the way up, a bunch of layers of rays coming out this way, red and black, and they're all oriented red. All the blacks are here, all the reds are here, all the blacks, all reds, all blacks, all reds. So they have the same orientation, and the right hand rule essentially made out of the fact that if you go dead down the straight middle, okay, right side north, left side south, that's all it means. That's all there is. There is no directionality. There's just the first movement is north and the first movement is south, and that just establishes the orientation of the field in terms of how a magnet will line up in it, because it'll always be a little bit stronger on the north end than the south end as it approaches, because there's always a tiny bit more south energy coming out this end and a tiny bit more north energy coming out this end because of that first ray. And that's the only bias that exists. I mean, they really just, you know, their theory is just wrong, and you know, they're not getting it. You know, what the iron filings are a lie. Okay, they're not really telling you what's happening.
Thus, the magnetic force is the centripetal force acting on the electrons.
It's not really true either. There's no centrifugal force here. It's clearly an external force. There's nothing tying it to the center, so to speak. There's no, you know, I guess they use centrifugal and centripetal, you know, but I'm not even going to get into all that crap. The point is there's there's clearly just the ring is big, the electrons are inside the ring, the light is shining on them, the force, and the force is in a direction towards the center, and that's the direction the electrons are being pushed towards, is the center.
This force that keeps the electrons moving in a circular path of radius r is equal to the field times the charge times the velocity of the moving electrons.
So, the mass times the velocity. So she's attempting to find the mass, so that's why she's converting the equation into one that doesn't have mass in it so she can get the mass.
Since V occurs on both sides of this equation, we can write this more simply in terms of momentum. And we have quantities now that we can measure. We can measure B, the field, by reading the current and using our calibration curve. The current in the coils is 0.79 amperes. That gives, for the field, 0.97 times 10 to the minus 22. So we have this for the field, and Q is still 1. And now we have to measure R.
I like also that she does the math by putting everything in brackets, just to be clear about what the thing is representing as a quantity, which is nice. I mean, even putting the 1 in,
Now, of course, we can't put a ruler inside the tube and measure R directly, so we have to use some kind of trick. There are a number of ways we could do this, but what I've done is this. I've taken a picture of the circle formed by the electron beam.
Yeah, she could have just taken a picture of the whole device, and she would know the distance, the radius of this thing, so then she could know the distances inside this. So she could have done it that way too. But what she did is clever enough.
Then I've removed the tube, and I've taken another picture of a scale put in exactly the same plane occupied by the beam. Here are the pictures. I've cut this along the scale, and now I can use it to find the diameter of the electron beam. The diameter is 11 centimeters, and R is half of this, 5.5 centimeters, or 0.055 meters. So here we have the momentum of...
So again, to me, this mathematics is all fun and fine, but I just mean the understanding the mechanism is more important, and that's where they fail. So it's nice that they can figure out that they can make deductions about how much energy it takes to move an electron, and therefore you know how massive it is by how much energy it takes to move it. So that's all nice and rational. But again, they're not really understanding the mechanism that enables you to see that.
Electron traveling in the particular circle that we've been watching. Now it's clear that from these two equations we can determine both the mass and the velocity. And when we do this, for the particular values we have here, we get the mass of an electron is equal to 0.89 times 10 to the minus 30 kilograms. Incidentally, the velocity in this case is about 6 times 10 to the 6th meters per second.
So obviously they can only do so much precision with this, and if you see her numbers, they're not, well, they should just, I may also play the whole video. Frankly, I mean, it's...
Here are the results of some other measurements that we've made with different values of V and B.
So you can see there's variations here that you know, technically these numbers should be all the same, so they're just averaged them out to get their number. So there's obviously a 5% error or whatever here.
Here you can see that although the accelerating potential varies quite a bit, and the field varies, giving different values for the radius of the circle and for the velocity of the electrons, still, the value that we get for m turns out to be always just about 10 to the minus 30. In other words, no matter how we do this experiment, we always get about the same value for the mass of an electron. We can also check very easily how the radius of the electron beam depends on the voltage and current.
So it's basically just saying the mass of the Earth dictates its orbit, blah, blah, blah. Velocity of the Earth dictates its orbit. So those two things are a factor in where the orbit's going to be. And for the electrons, you all have the same mass, so velocity is everything.
You can see that by increasing the voltage, and thus the energy of the electrons, we make the circle larger. Increasing the field makes it smaller.
More light shining on the electrons, more force.
In fact, if you want to do a little algebra, you can find out from these two equations.
I don't know why YouTube does this crap. No, there's nothing wrong with my connection, YouTube. You just suck.
How R should vary with V and B. Finally, let's do one more thing. So far, we've been shooting the electrons straight up, perpendicular to the field.
So again, it's not perpendicular to the field. The field is, again, pushing this way evenly in all directions. So the field is pushing towards that center.
What would happen if we were to shoot them at an angle so that there would be a component of their velocity parallel to the field as well as one perpendicular?
So now they're not going to be flying. They're not going to have a center in the center. It's another way to say it. They're constantly going to be moving this way through a force that's coming in this way.
I will rotate the tube like this, so that the direction in which the gun is aimed will make different angles with the direction of the field. The vertical component of the electron velocity will still be affected by the magnetic field, but not the horizontal component. Here, the gun's direction is at right angles to the field. As I change the angle, the electrons continue to circle.
So you can see that now the circle is not connecting, because the deflection is now going to be uneven. And you're creating a precession in the spiral because it doesn't have a common center of gravity.
Direction of the magnetic field, but also move along the direction of the field until they hit the glass.
Right, so they're not really moving in the direction of the field, they're moving in the direction you've pointed them in. So the precession is in the direction you start them in. If you start them this way, they'll process this way. If you start them that way, they'll process that way. So there's no moving in the direction of the field. It's just incorrect. Alright, I don't know if I need to play any of D. Hilster beyond the fact that, he just makes this video and he basically says, no, I don't buy it. Electrons don't have a mass. He thinks they're all made out of this G stuff. The electrons and the photons, he's saying, are the same thing, which can't make any sense. The force isn't the same as the thing it acts on. I don't know how he can make that make any sense at all. Then you have to have force hitting force. He actually says that in the video, as if photons interact with photons and they bang off of each other, when you know that isn't the truth. You can't get a laser beam to deflect a single photon ever. This is, you know, it's just not a sensible argument. Especially scatter. You cannot scatter a force with a force. Forces do not interact with forces. Stuff going the speed of light does not interact with stuff going the speed of light. So, you know, I could just critique what he's saying and say it's just bad and stupid and wrong. Because it's just bad, and it's just, there's so many glaring contradictions in what he was saying, and they're completely inconsistent with what gravity really does and what magnetism really does. So it's just wrong premised all over the place. So let's go to the 60 symbols video, which I think is here, and it's just so bad.
Make this equal 101.
So what we have here is a ball, and you imagine if I take this ball and bounce it off the table, it'll bounce off that table, and if I do that exactly the same way each time, then what will happen is that it'll hit the same point on the...
Right, so, you know, I don't know why this is called electrons, and it's really just about diffraction and, you know, patterns, interference, which isn't the story of electrons. And so the very idea that he says, so if I take this and bounce it off of a table. So again, this is a key fundamental misunderstanding of physicists. There are no tables in the electrons world. There's no such thing as a flat end surface, a big giant flat surface that I bounce off of, and I can possibly bounce off the same location twice in a row. The electrons are deflecting off of other electrons, and they're not hitting the other electrons. They both are have a field of energy, and they're repulsive to each other's fields. They never hit each other. They deflect off of each other. They feel the field the other one is producing, and it's a compression field. It creates high pressure. Lots of ping pong paddles with little ping pong balls flying out. As you bring the paddles closer and closer together, the balls start bouncing really, really fast. They deflect off each other. And, you know, so, I mean, the way they're illustrating the physics is just so wrong. There's no surfaces in the atomic world.
Imagine if we had 1 million balls, we could control it so that each and every one of them hit the table in exactly the same way, exactly the same velocity. They'd bounce off, and we'd end up with a very well-defined...
Obviously, you can't do that, right? Obviously, you can't hit the same exact electron in exactly the same position, right? So they'd never have any such circumstance. You're always, if you miss the electron the second time, it means the thing's going to travel in deeper, hit some other electron that's going to be at a different angle in terms of its position, and you're going to get a different angle out.
Wall. Okay. If we then, for example, just scatter those balls, take them and fire them off at different angles, then what you'll find is that the wall will cover up with different dents in the wall, and we'll end up with a sort of random...
I mean, this physics is so juvenile. You know, I mean, 60 symbols sometimes is pretty intelligent and pretty sophisticated, but this is such a grammar school description. It's just so bad.
A random distribution of dents in the wall.
Electron is a negatively charged particle, and it is enormously important. Mendeleev didn't believe in electrons. He thought atoms were solid and you couldn't break them.
Who cares? You know, I mean, there's lots of people believe lots of wacky crap. Clearly, Tesla believed that there was, you know, gigantic flows of ether all around us, and that we could just, you know, tap into them and have, you know, tremendous amounts of, we could realize tremendous advantages from all this huge force, you know, that we could tap into. And you know, quite diluted. You know. So anyway, we can just name all of them and point out how they got something wrong.
Made up of anything else, and he believed this till he died in 1907. But electrons are enormously important for chemists.
So now, if we imagine instead of we're in the real world.
So this is just so broken up too. It's just such a horrible way to describe what's the function. It doesn't get to any of the essence of it, that the electron is one of these elemental bits, that it is indestructible essentially, and that it is completely owned by this electromagnetic radiation. It is, you know, it goes where the radiation tells it to.
Shrink everything down so this ball becomes an electron, and we can think of this as being an electron. What we actually find, remarkably, is that we get these bands. We get this very well-defined pattern of here where there are lots of dents, here where there are practically none, here where there are lots of dents again. And those bands have a well-defined spacing, a well-defined separation.
Yeah, the simplest pattern in the universe you could possibly make, on, off. Essentially, I could describe it again as if the electrons, the atoms, are in positions, and if you miss this electron, you're going to hit the other atom's electron. It's going to be lower because they have to be lined up, you know, appropriately because of their polarization. And so the angle is going to be different because this one's in a different position. It's at a different pressure. Lots of reasons you're going to get a different angle out. So you get two different angles. And there you explain the pattern.
Do electrons behave so differently from little balls? And maybe that's because, well, actually they're not little balls. There's something different from little balls. What could that be? Well, let's go down to the...
Let's use, you know, let me use the magnetic example again too. Because you could sort of get this in a drawing, I think. I mean, if you understood that, you know, combining atoms, you know, the atoms are lined up, and the electrons would all have a position magnetically. Okay, they'd have a little bit of a orientation to them, you know, a little bit of a shape. A very good drawing. And so, you know, this is the atom, the protons, whatever. So the electrons are always going to be on the surface. And so you can sort of say, you know, that their positions, you know, they have set positions. And you could hit this electron, and you're going to get a certain angle out. You hit this electron, you get a certain angle out. You hit this electron, you get a certain angle out. You know, and likewise, if we just move the position of this down, because these are repulsive, these protons, and we have to move this one up, you know, you can get a lot of variation in this shape. So the shape of the surface is, you know, something that has this wave form to it, all right, and it's that shape that's creating these various angles. The fact that you're hitting the waveform in different places is creating your angular differences. It's the surfaces that are causing the phenomenon. This isn't a function of photons and electrons. Interference is not a function of the little bits. It's a function of the thing the little bits are interfering with. They're being interfered with by hitting things in different positions and at different pressures. And they're just, it's to me so obvious that this should be at least considered. They don't even consider the surface. Again, they're bouncing off a table saying this is an illustration of what electrons do. They bounce off of tables. They don't bounce off of tables. They bounce off of the little nuclear bits inside an arrangement of atoms. And those little nuclear bits are not a table. Am I still recording? Yeah. Okay.
we'll see another experiment whereby we see these patterns, and maybe the patterns we see in that experiment will help us to understand really what they...
Yes, no, that's exactly, you just keep making the same mistake. I'm going to compare photons to water, I'm going to compare electrons to photons, and I'm going to compare buckyballs to electrons, and I'm going to compare radar energy to electrons, even when there's no slits. I'm still not going to get it. Even when there's nothing for them to bounce off of, I'm still not going to get that it's not interference. Just jamming. I mean, it's a kind of interference, but it doesn't have anything to do with photon plus photon. It has to do with competing frequencies.
Right.
When I teach the students...
So all this drama that they're going down to some brilliant lab and do some brilliant thing, he's just going to do a 2-slit experiment, right? And you know, so they're just making this more, let's make it into a mystery, let's make this into some sort of high-tech thing. No, when it's incredibly low-tech, when it's something Newton had already discovered. It's as old as Newton. And they're pretending it needs to be, we can only have a quantum description of this reality.
In their first week of coming to university, I tell them about electrons, how they behave in atoms. And they find this is very...
So this is the whole problem, right? I tell them that they're wooey things that don't know where they are, and they're in some sort of orbital thing, and it's blah, 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 but they have no location, and you have to consciously look at them, or they won't have a place in the universe, and blah, blah. Instead of just saying, no, they're essential to the bonding between atoms. Clearly they have charge. The most outstanding feature of the electron is the fact that it's oppositely charged to the proton, and that essentially it is a magnetic monopole. That is the most outstanding feature of the electron. But instead they do all this wooey crap. So of course, if atoms are sharing an electron, that is, they have these things orbiting around them, stuck magnets. Now, I sort of explained, you can do this with a piece of glass. You can put magnets going all the same face, and you can create essentially your own atoms. If you have some mechanism that prevents the magnets from flipping, you can get them to stay in rigid positions. No matter what gravity you put them in or whatever you do, they'll stay in those positions. People got, you put magnets on a stick and you get them to hover. I mean, it's an essential force, and that's the binding force. Of course, if two atoms are sharing electrons, the electrons are right there, the two atoms are sharing them as part of their tension. The tension of all their other electrons are dependent on those two electrons. Obviously, breaking them apart is going to mean one of the atoms is going to be broken significantly. So yes, it's a strong bond. 2-electron bond. Strong bond.
Because electrons, if you treat them one way, behave just like a particle. An electron is something, a negative charge that can be transferred.
So this is the horse crap, right? It has no wavelength. They just made it up. It has a momentum. It has a velocity. They called it a wavelength. They gave it a fake identity, a fake notion that somehow it has a frequency when it doesn't have one, that it has a period when it doesn't have one. I mean, it's all convoluted mush. There is nothing but particle characteristics. Because it creates a pattern, you've made this silly assumption that it's a water wave. It's not water. It doesn't live in water. It doesn't behave as if it lives in water. Why are you making this assumption? There's none of the physical features that create water waves that could at all be applicable for photons and electrons. They're not affected by friction and other notions.
Between one atom and another, rather like changing money.
Yes, they can transfer electrons, but more importantly, they can transfer the pressure between the electron. The electron can vibrate here, move a little bit, and it causes this electron to move a little bit, and the next electron to move a little bit. What they can do is transfer the pressure. The paddles, the ping pong paddles, ping pong balls bouncing. I have another paddle over here, ping pong balls bouncing. I have another paddle next to that, ping pong balls bouncing. If I accelerate the bounce rate on one of the paddles, in between these two paddles, the fact is that's going to bend this paddle a little bit this way, and then that's going to cause this paddle to bend a little bit this way, and that's going to cause the next paddle to bend a little bit that way. That's what electrons can do. So you can, yes, you can throw it. You can move ions across a surface. You can create ions going across the surface, or you can just transfer the pressure from one atom to the next, and that's electricity.
On the other hand, if you want to understand the structure of the atom, then you have to treat the electron as a wave.
Nonsense, just absolute nonsense. If you treat the electron like a magnetic monopole, you've solved your problem. And you treat the proton like a magnetic monopole, you've solved the problem. There's nothing to figuring out what an atom's doing. It's just a balance of pressure between the two. If you understand that there's two forces in the universe, a plus force and a minus force, a south force, a north force. I mean, they're just so wrong.
Hello, George. What we have here is not an experiment with electrons, though we'll get to that. What we have,
Oh yeah, you'll sort of get to that. So here they're doing an experiment with photons to somehow explain electrons. It's just bogus.
is an experiment with light. And
This is perfect, right? So this is a really good illustration of the pattern. So he just did this whole thing. You get a dark band, a light band, a dark band, a light band. Is that what you see there? No, I see a clump in the center and then another clump away from it, another clump away from it. I see bands, but I see a secondary pattern. What's that about? Where did you explain that with your ball example? How is that happening? What's causing that effect? Maybe it has to do with those other surfaces, right? 4 surfaces that you shot the light through.
So we've got a laser. The important reason we're using a laser and not, for example, a light bulb is that in a laser, the photons of light all come out in step. So we've got a...
So more nonsense, right? No, you're not using a light bulb because you don't want to do it with, you want monochromatic light. Yeah, clearly the more intense the beam, the clearer the pattern is. But that also illustrates the point that the pattern looks very on-off. It looks like little dots you have there, don't it? Those look like actually a duplication of your laser beam, don't they? They look like the same light hits different places and it just sends a copy of the same image to different locations. So that's all these are. These are just images of what goes into the slits. It's just an image. One image goes here, another image goes here, another image goes here, another image goes here. They're just images.
Through which those photons, those little packets of light, have got to pass. And so if you follow this through, you follow the path of light. Down here, we have the light. And instead of it all piling up, what we see is this pattern exact.
Yeah, so it's the exact. You hear the words, the exact pattern. It's not the exact pattern. It's completely unexact. It's not even really close to exact. It's very fundamentally unexact. Again, why aren't there little circles of dark space? Why are there circles of light and there aren't circles of dark? If it's supposed to be some sort of an even amount of constructive interference and an even amount of destructive interference, shouldn't they both be circles?
That I was discussing in terms of the electrons. And this is something called a double slit experiment. We have 2 slits here.
Right, so they show water waves, and again, there's no double pattern in those waves.
The key thing here is that what we have is light. Light is a wave. That wave is...
And actually in the water waves, the pattern does change with distance. I mean, it does get substantially, the waves stretch out because of the friction of the medium. The ones in the center are actually smaller bars, and the ones further away are wider bars. Much wider. Wider than they are in light. Because of the fact that there is tension in water. Friction.
And it's interfering. Constructively, destructively.
The longer you travel through, the longer distance you have to travel, the more the wave gets compressed by the fact that it's pushing against an opposing force.
Type of pattern. The key thing here is related to how those waves interfere with each other.
So the key thing in here is to say something's exact when it's nowhere even close to exact. And, you know, just to pretend that we have nailed it, we've got the right answer. This is proof solid that this is the same phenomenon, when I think quite obviously there's enough difference there to say something else is going on.
See, exactly,
Exactly, right? You know, Screw the reasonable definition of words. Not really even close to exactly. Water doesn't create little round circles. And again, why are the circles there? Why aren't there circles for the destructive interference? Shouldn't the destructive interference be little circles too?
Pattern in terms of this, these bright spots, these dark spots, when we do this experiment with electrons. And that leads us to think, well, hang on, if we're seeing...
Yeah, so again, and electrons won't be the same because electrons won't do this clear light-dark thing. They're going to do a blended, nice blended light to dark, light to dark, light to dark. Because again, electrons are deflecting. It's a much softer process for electrons. A lot more variation in the process because of the fact that it's a deflection off of a compressible force. So there isn't a hugely... the event is a longer event, which makes it more variable based on momentums of the two objects. So the momentums start to matter a lot more for electrons. More momentum, more compression, different angle exiting. So any subtle changes in the movement of the momentum of the electrons will create much more variation in their pattern, and that's why it's a much softer pattern.
The same patterns with photons, which are a wave, and we know that as electrons.
Again, we know that. You don't know that. You haven't proven that. Your evidence is incredibly weak. It's lame. It's pitiful as evidence. The simplest pattern in the universe, and every time you see it, you're going to say it's interference. You know, on off is, you know, somebody turns the light switch on. It's an interference pattern. No, it's not.
Then it leads us to think, well, maybe the electrons are actually not just little hard balls, little billiard balls. They actually have a wave-like nature.
That they have no form, shape, description at all. They're somehow, you know, because we'll give them no position, we'll make them waving because they don't have a position or something. But clearly they have no frequency. They have none of this stuff innately. It's just nonsense. It's just made up. They have a speed. They're cannonballs, and again, because they don't have the vision to be able to see the cannonballs very well, they're just assuming, you know, it's a wave of cannonballs. But that's not even the way to put it, because here clearly you can impose a frequency on electrons. You could fire them at a frequency, a blob of them and a blob of, you know, I could shoot cannonballs, 10 cannonballs, no cannonballs, 10 cannonballs, no cannonballs. I can make a wave out of cannonballs, but cannonballs just thrown around in chaos don't have an innate frequency. They have no innate period.
The problem is that you have to explain the thing mathematically.
Nonsense. You have to explain the thing geometrically. There's an algebra to it. There's a physical reality, and again, they're just bailing on physical reality. Heisenberg it all to pieces. But there is a truth. The electron has one path, and their math even tells them that. Okay, and so that is the truth. There's only one path back. If you had to do it, reverse the experiment, there's only one path back.
And as soon as you go into the maths, the difficulty is that unless people are very good mathematicians, and I'm not, it's not very clear what the equations mean.
Everyday common...
Yeah, they don't mean anything. They're just formalizations of an effect, and you change the equations to suit the experiment. So when you're doing the two-slit experiment, the variables mean one thing. When you're doing the single-slit experiment, you just change the meaning of the variables. There's nothing... The mathematics is telling you there's something wrong with your theory. If you have to change the variables, there's something wrong with your theory.
Does not allow us to describe it in simple words. The concepts are too elusive and slippery for the English language. But
no, the concepts are too stupid. They're too undercooked. They're too fetal. You don't name the fetus. All right, you've decided the fetus is something, you know, and no, it isn't yet. It's not a hatched egg. It's not its adult form. Okay, it's underdeveloped. And you're taking your underdeveloped notions and turning them into facts, and that is just so unscientific. Newton would be ashamed.
Its particle-like qualities, which it always takes with it, such as its mass, its momentum, its spin.
So spin is bullshit. That's more quantum crap. They just invented that notion. Spin is a metaphor for electrons have a wobbliness. And their wobbliness means they have a history. That's what's causing it. So the fact is, it matters to an electron what happened to it a minute ago, is it has a certain amount of energy inside of it, and so it has a weakness to a direction. It has a bias, just like the bias of the coil heading the right-hand rule. The electron has its own little rule that's dependent on where it was a minute ago and what it was doing, what kind of environment it was in. And that bias means that it has a tendency to go left or a tendency to go right because of what happened to it previously.
Lepton number, and so on.
There's no lepton, that's just nonsense.
And that always remains. So if a particle comes along and hits something, that is always conserved, and this quantity remains the same. But when it hits things, it does so as a wave, scatter.
No, it does so as a cannonball with a force field around it. A cannonball radiating an energy that's repulsive to other cannonballs. It's ping pong paddles with ping pong balls coming out of them. And the paddles find it repulsive. This paddle is producing ping pong balls. So just think of it that way. It's producing them. And this paddle is producing them. And the closer you bring them together, the more balls that are hitting the paddle, the more reflections, the more repulsive they are. So the paddles can only deflect off of each other. You need high energies to actually create enough momentum to push through that force and actually have something you might consider an impact. But I still don't think you actually hit them. You just create more pressure, which means the tighter the pressure, it means the higher the frequency, that means you're creating X-rays and gamma rays and all kinds of high frequency energy.
Things as though it were a wave. So all the time it has these two elusive characters going on.
It doesn't all the time. In 99% of experiments, it has every appearance of being a corpuscle, a clump of energy, a quanta of energy, and only in these experiments where you make it interfere with atomic bits does it have any of this strange behavior. And instead of concluding the material you're putting the electron into is the thing causing the effect, you sit there and blame it on the electron. It's just that bad. You have this complex matter to blame, and instead you blame the dumb electron.
I don't know. Physics, when you're 18, is based on common sense, but when you've gone through all this, somehow you get used to it. You don't actually like it. You just get used to it. And
yeah, whatever. Yeah, you get complacent with a bad theory, and you just keep spouting it. You have a wrong answer, and you just say, well, 3 is almost 4, so I'll just pretend, yes, 2 plus 2 equals 3. Okay, alright, if I have to say that, I can say it if I have to, but yeah, it doesn't sound right. I mean, why don't you admit that? Why don't you just admit that this doesn't sound right, and there's probably a righter answer. There's probably a better answer than 3.
live with it, and that's the language that seems to fit.
It doesn't only seems to fit because you all are in the same fucking Furby suit. So yes, you've all gone to a party and decided to be squirrels. And it only seems to fit because, yeah, well, if I take my suit off, everybody will be looking at me. It's like being the only naked guy in the room or something. Yeah, I don't know, I feel awkward. And so you're afraid to take your suit off.
So back in the office, what we were doing was this, considering that if those electrons were billiard ball-like particles, that when we fire them at something, they'll all pile up in one place or they'll spread out randomly. What we have here is the actual experiment where we're taking a sample and we're firing electrons of that. Those electrons are bouncing back from that sample and we're looking at the pattern they form. Now,
right, and there's again, he's going to blame it on the electrons. So he's overtly telling you, I'm taking electrons and I'm shooting them not at a sample, a table. I'm shooting them at a complex arrangement of atoms, a material, and each material has a different arrangement of its atoms, which means there's a different arrangement of the electrons, and it means the electrons are in different pressure, in different locations. And I'm going to blame the electrons for the pattern I get back. how can this? I mean, he's almost describing an electron microscope. He's almost describing an electron microscope. Do you expect when you shoot the electrons at the object you've created to reflect them back to you, showing the shape of the object? Do you really expect that the electrons would reflect off as just a blank piece of paper? That it's the electrons that create the pattern, or the surface that they're being bounced off? What could, if I put a microbe, or it's they're usually a small little bug. I put a little small bug, a mite, inside the electron microscope. I do understand, right, that it's the unevenness in the surface that creates the pattern of an image. The electrons don't do it. It's the irregularity in the surface that did it. So why wouldn't he blame the irregularity of the surface for the pattern? Why is he blaming the electrons?
Little billiard balls, and we wouldn't expect to see, what we'd expect to see would be a random sort of splurge of electrons.
Yes, if we were dumb enough to think that the little thing you're looking at, the little tiny amount of space that you're shooting and hitting, is somehow a table. That somehow matter is made out of tables. That this pen has table all over the surface. It's all just flat table. There's no atoms. There's no electrons. There's no nuclear bits. It's just table. I mean, this mistake is so glaring, and their avoidance of analyzing the fact that the surface has the character. The surface is the complex thing. The electron is the simple thing. The surface is the complex thing. You see how they're overtly avoiding conversation about the character of the surface. This is such a pitiful reversal of roles.
That's not what we see. What we see are very, very well-defined peaks, and those peaks and spots arise from the wave-like properties of the electron.
No, they arise from the surface irregularities of the substance you hit, and that pattern will change depending on what substance you shoot the electrons on, and you know it. So why are you pretending you don't know that? That pattern is completely dependent on what you're hitting.
We have here is, instead of having a slit like we had with the experiment with the photons of light, what we're using, because the wavelength of the electrons is so much smaller.
Again, they don't have any wavelengths. Again, just a preposterous lie. They have a momentum, a velocity. That's it. They have mass and velocity. They don't have any wavelength. That's a made-up number, a made-up notion. They are not moving at a regular spacing. They're not doing any of that crap. It's just a complete lie to say they have a wavelength.
Is we're actually using the atoms at a surface to diffract the electrons.
Yeah, there you go. Well, that's what we're actually doing, but I'm not going to tell you. Oh, I did tell you that? Oh, my bad. I shouldn't have said anything about the surface. I mean, this is so overtly stupid.
One of the things which I think perhaps students find particularly difficult is that when you're treating the electron as a wave, you can't really talk about it being there or there or there, because a wave...
Yes, right, because that's just another huge flaw. You should just say to yourselves, oh shit, if we can't locate these things, then we're really losing the idea of physics, aren't we? That's magic, isn't it? If we're just going to pretend the little bits... So unlike everything else in the universe where we can see it, okay, and it's in a place, the stuff isn't... We're not pretending Saturn's in 3 different locations at once, or it's hopping around or doing any of that bullshit. So unlike the rest of the big universe, when you get to the little universe, all of a sudden the rules change. So the stuff we can't see is the stuff where you make the magic happen. Isn't that convenient? There's no magic. Oh, it's just pitiful.
Is everywhere in the volume that you're considering, and therefore the idea that everything is very delocalized is difficult for people to understand.
It's stupid. Why would I bother understanding it? Because it's just a God theory. It's an invisible man theory. We have magical properties for electrons. They don't behave in this mechanical way. Of course they are behaving in a mechanical way. That's why you get consistent results, and you're just being obnoxiously imprecise. This is just such bad physics. And you had the evidence again. If there was a lot of evidence for this woo, then you could maybe there could be an excuse for it. But the evidence is pitifully weak.
Back in 1923, there was a piece of kit who resembled this that actually gave us really the fundamental proof that electrons had wave-like characteristics.
Nonsense.
And so it was a couple of people called Davison and Germer managed to measure a pattern just like this that we've got in here, very similar to this, and they realized, well, hang on, that's a diffraction pattern. That means...
See, again, any pattern is just going to be called a diffraction pattern. And yes, diffraction would be fine, but again, what are you blaming for the diffraction? You know, you're blaming the electron, which is the stupid thing to blame.
Electrons must be waves, or must have wave-like character.
No, they must be able to interfere with themselves or each other, and clearly they can interfere with each other, but you know, you're gonna have a hard time making that happen without beams shooting into each other. Which would also be an interesting experiment to see, because electrons really should do quite a bit of scattering, unlike light. You should be able to see the clear difference between a beam of light and a beam of electrons by doing the shoot them at each other thing, because you'll see with the electrons that there'll be a lot of scatter. Oh, more scatter. They're still very small. Obviously, it's still hard to make an electron deflect off an electron. So it'd have to be a beam of an awful lot of electrons, pretty dense beam of electrons. So I shouldn't have said it quite that way. It's not that easy. All right. But terrible, just an awful video. Just awful, awful, awful. I don't know why they leave this up. They ought to redo this subject. This is their video on electrons. This piece of steaming crap. Just horrible. Horrible. Disgraceful as an explanation of the real role electrons play. It was, you know, interference is a tiny. Even if it was even if it was a real phenomenon, it's a tiny amount of time electrons are doing that. Their interactions are much more numerous not doing that. So anyway, I think that's it. Yeah. So, long video, and so till the next time, hopefully properly saved and such.